Welcome back, everyone. This is Professor Herring. In this video, we're going to continue our discussion of thermochemistry, specifically looking at calorimetry. Let's begin. So calorimetry is kind of a subset of thermochemistry. Calorimetry is where we're using experimental methods to measure heat flow. And we've already seen a lot of these ideas earlier. When we calculated the heat changes for chemical changes or for physical changes for states of matter, when we converted a substance from a solid to a liquid to a gas, etc., we already used this relationship. The only difference here is that instead of talking about just a physical change, we're now also talking about chemical changes. And so we need to account for chemical reactions. This adds a new layer of complexity to the problem-solving process. So we've already seen this equation before. You're already familiar with it. Something to note is that when we're doing these reactions, what we're talking about is taking typically a cup of water or beaker of water and adding some kind of salt to it, and it dissolves, and it either gives off heat or absorbs heat. And so we need to talk about the system and the surroundings. The system is usually going to be the chemical reaction that's occurring, whereas the surroundings is anything from the water to the cup, and most importantly for thinking about this is the thermometer. So remember that since the thermometer is part of the surroundings, that when the thermometer sees that the temperature goes up, the thermometer gained that energy. So it was endothermic for the thermometer, but exothermic for the reaction. Conversely, if the temperature goes down, then the thermometer lost energy and the system gained energy. And so we would say that that's endothermic. These particular concepts are very commonly misunderstood by students. So you want to make sure that you're paying attention to the fact that the thermometer is part of the surroundings, and that when it observes a temperature change, then that it's observing it for the surroundings. Finally, this is just stating the relationship that the energy absorbed or given off by the system is conversely taken by the surroundings. So if our surroundings absorbs 10 joules, then the system gave off those 10 joules. And we call this a coffee cup calorimeter. In actual chemical labs, they use what's called a bomb calorimeter. And we actually have some at Penn State here at University Park. So if you're ever around, you can go up and ask if on the third floor in the Whitmore building if they will show the bomb calorimeters to you. And as long as they're not in session, they might be able to do that. So let's do an example. We're mixing solutions here. So this is again looking back at chapter 15 for solution chemistry. So we've got hydrochloric acid mixed with sodium hydroxide. The temperature increased from 21 to 27.5. Calculate the enthalpy of reaction in kilojoules per mole for hydrochloric acid, assuming that the calorimeter doesn't lose any amount of heat. We're given the total volume of the solution, the density, and the specific heat of the solution. So let's make sure that we're first identifying whether or not this is endothermic or exothermic. So again, we are talking about the temperature went from 21 to 27.5. And remember that when we look at temperatures, it's from the perspective of the thermometer. So keep that in mind and think about this. Okay, what did you determine? Well, If it's going from 21 to 27.5 for the thermometer, then the thermometer saw that it was endothermic. It was endothermic for the thermometer, then it was exothermic for the reaction. So it's A. That means then that the water actually is releasing the heat, or excuse me, the water is absorbing, and that the products are lower. So there's a general approach to solving these types of problems. The first step is to write out the balanced chemical equation, identify the amount of reactants involved in the system, and draw some pictures. Then we want to calculate the heat transferred by the system, and then calculate the heat of reaction per mole of reactants or products, depending on what it's asking for. So within this, we have to remember to account for the limiting reactants. So you should be able to write out a balanced chemical equation for this problem. Try it on your own. Welcome back. Did you get this one? I hope so. The hydrochloric acid would be aqueous, sodium hydroxide would be aqueous, sodium chloride would be aqueous, and the water would be liquid. So now let's start with the information that we're given. We've got 50 milliliters each, sodium hydroxide and water, and they're both 1 molar. We will use the molarity to find the moles. Remember that molarity is equal to moles of solute per liter of solution. Therefore, the moles is going to be equal to molarity times the volume in liters. So, the moles of the hydrochloric acid is going to be equal to 1 molar times the volume in liters, which is 50 times 10 to the minus 3. That gets us a total of 0.05 moles. We do the same process for the sodium hydroxide. We see that it's also 1 molar with 50 times 10 to the minus 3 liters, or 0.05 moles. Hopefully at this point in the semester you should be able to see, because they're equal and it's a 1-to-1 ratio, that both run out. They run out equally. And so we can use either of them to, we're not going to have any leftover reactants. Okay? Now, what we can do, knowing that we're talking about the energy per mole of hydrochloric acid, we're going to use the moles of hydrochloric acid. So we need to now calculate the heat that's involved. We know the temperature change. We know the specific heat of the solution. And we know the volume and the density. So the specific heat is provided there. To find the mass, we need to use the volume of the solution times the density of that solution. Now, notice that in this case, we're going to use the mass of whatever we are measuring. So since we're measuring the temperature of the whole solution, we have to use the mass of the whole solution. Okay, so that's going to be 100 grams. The change in temperature is the 27.5 minus 21. Now, you might have noticed that this is degrees Celsius, whereas this is in degrees Kelvin. But remember, when looking at the changes in temperature, degree Celsius is equal to degree Kelvin. To prove that to yourself, take and convert 0 degrees Celsius, and let's say we wanted to go from 0 to 273 degrees, or rather, excuse me, 0 to 100 degrees Celsius. Find the change in temperature, both for degrees Celsius and Kelvin. and you'll find that they are both exactly 100. So our change is 6.5. To find the heat of the surroundings, that's 4.18 joules per gram degree Kelvin, the specific heat, times the mass, times the change in temperature. And that's equal to 2,717 joules. That's the heat that's absorbed by the surroundings. The heat that's given off by the system is just the negative of that. So to find the enthalpy of the reaction in kilojoules per mole of hydrochloric acid, we're going to convert from joules to kilojoules and divide by the number of moles of hydrochloric acid. So we take the ratio, convert from joules to kilojoules, and we get that this is equal to negative 54 kilojoules per mole. Note that it is standard for all enthalpies of reaction to be given in terms of kilojoules per mole. All right, now that I've showed you how to do one, you try this one on your own. So pause the video and try this before watching the solution. Welcome back. So ammonium nitrate is, in addition to being a fertilizer, it's used in cold packs to ice injuries, and that's because it's an endothermic process when it dissolves. So we're given, we want to know the final temperature when we dissolve a certain mass of ammonium nitrate in water. We're given the initial temperature, and we're told that the mass of the solution is the sum of the masses of the solvent and solute, and we're given the specific, or the heat capacity of the solution. So in this case, we don't need to worry about a limiting reactant because there's only one reactant. So we can go right away. We know that we're going to need to find there we go. This is our equation that we're going to use. We're looking for the final temperature, so we need to find the change in temperature. We're given the mass of the solution and the specific heat, and we need to find the heat that's involved. Remember that the Q of the reaction is going to be equal to the moles times the enthalpy of the reaction. Okay. Notice that this is very similar to when we talked about Q equals N delta H for things like vaporization or condensation. It's the same relationship. So since we're given the enthalpy of the reaction, this is for per mole of ammonium nitrate. So we need to find out how many moles of ammonium nitrate we have. We can do that by taking the mass over the molar mass and get 0.3088 moles of ammonium nitrate. To find the Q of the system, that's going to be the moles times the enthalpy of the reaction to give 8.276 kilojoules. To solve for Q of the surroundings, we need to take the negative of the Q of the system. So that's negative 8.276 kilojoules per mole. And again, the reason for this is because we are, in one case, we're measuring the temperature with a thermometer, but it's being given off or absorbed by the reactants. So our Q of our surroundings is equal to Cm delta T. Our mass is the sum of the masses of the solute and solvent. And to find the change in temperature, we rearrange and plug in our values. And when we do so, we get that it's changed by 10.44 Kelvin. Now this is the change in temperature. So if we want to find the final temperature, we need to account for the fact that the change is equal to the final minus the initial. So to solve for the final, that's going to be equal to the change plus the initial temperature, or negative 10.44 plus 21.6, for a total of 11.2 degrees Celsius. Okay, that's it for this video. Thanks for watching. If you have questions, you can ask on Piazza, in office hours, or recitation. See you later.